and then this will be our depth for the x-axis. So Ixx, so the width is 6 d cubed over 12 minus by the internal, the width is 5.5, the depth is 2.5 cubed over 12. Okay, so 6 times by 3 power 3 divided by 12 minus by 5.5 times by 2.5 power 3 divided by 12 is equal to 6.338 or 339 inch to power 4. I will do it again. 2.5 power 3 times by 5.5 divided by 12. 6 times by 3 power 3 divided by 12 minus by this. 6.339. Okay. So the next one we want to find IZZ. So now the axis of interest. This is the axis, right? This is our ZZ. So this geometry will be our width. This geometry will be our depth. Okay. So now it changes. So now IZZ. So the width is 3. The depth is 6 cubed over 12. And then minus by now the width is 2.5. The depth is 5.5 cubed over 12. So this will be equal to 3 times 6 power 3 divided by 12 minus 2.5 times 5.5 power 3 divided by 12. 19.339. Okay, this is 19.339 inches to power 4. Okay, so let me check again. 3 times 6 power 3 divided by 12 minus 2.5 times 5.5 power 3 divided by 12, 19.339. Okay, so we have we have our IZZ, IXX, IZZ, IX. Next is our A, okay, our cross-sectional area, okay, which is equal to 6 multiplied by 3 minus by 5.5 multiplied by 2.5. Okay. I don't think we need it, but I already said that I'll be doing it because we don't need it because there is no PY. Okay, I'll do it again. 4.25. Okay. So now I have all this value. Okay, so now let's calculate the normal stress for element A, B, and C. Okay, so the formula, I'm going to copy this. Okay, so we call this our X, Y, Z. And we know that our moment in X is equal to what? Our moment in X is equal to oh, I do apologize, I did not do one more step down here. So we know that this is our moment in X, and all of them will be under compression. Okay, right? It's going that way. So element A, B, C, okay, element A, B, C, all of them will be under compression. Okay. So we know that they are all in compression. So Mx is equal to 30,000 pound-inch. Mz, and because of our analysis, we also know that they are all going to be in under compression mode. So it's 60 times 10 to the power 3. Okay. So now we again we drew our cross-section view. right? So this is our X, and this is our Y. And then we have our element A, which is exactly at the corner. Element A, element B have a certain distance. Element C has a certain distance. Okay. So we look at the normal stress first. Okay. So we look at stress Y, which is equal to mz. Now we know that everything will be minus, right? Because moment in X will induce compression for all of them. Moment in Z will also induce compression. Okay. Now the thing you have to be careful is what is the X and Z direction or distance. Okay. Right. So first we do element A. Right. So element A, what I tend to do is I tend to write out the distance first. So the X from the centroid is equal to 6 divided by 2. So this is equal to 3 inch in X direction, right? Then in Z direction, it is equal to 3 divided by 2, which is equal to 1.5. So stress Y for element A is equal to mz mx, right? So we know it's compression, so we put in negative. Multiply by z, so z is 1.5. Divide by the ixx, and our ixx is equal to what? Ixx is equal to 6.339. Okay. And then we have minus mz multiplied by x distance, which is 3, and then divide by izz. Izz is equal to 19.339. Okay, so this will be equal to 30 power 3 times 1.5 divided by 6.339 plus by 60 power 3 times 3 divided by 19.339. So I get 16.407 times 10 to the power 3 psi. Okay, let me do it again. Yep. Okay. Then the next one is we want to find point B, element B, normal stress. So element B, there's an offset of 0.25, right? So it's equal to 3 minus by, in the x direction, by 0.25. Is it 0.2? No. Yeah, it's 0.25. Is it 0.25? Yeah, 0.25. So it's equal to 2.75 inch. And then the Z, A, B, and C, the Z distance are the same. It's 1.5 inch. Okay. So stress Y at point B is again minus 30 times 10 to the power 3 multiplied by 1.5 divided by 6.339 minus by 60 times 10 to the power 3. So that's mz 2.75 divided by izz is 19.339. So this will be equal to 30 power 3 times 1.5 divided by 6.339 plus 60 power 3 times 2.75 divided by 19.339. I get minus 15.631 times 10 to the power 3 psi. Let me do it again. Okay, 30 power 3 times 1.5 divided by 6.339. Yep. Okay, and then finally at point C, the x distance again is equal to at point C. So 6 divided by 2 minus by 0.25. Oh, this one will be equal to 0. Minus 2.75. So this one will be equal to 0. Okay, so the x distance equal to 0 means it's on the neutral axis. Okay. And then z, no change, is 1.5 inches. Okay. So we do stress y is equal to mx. Okay, so mx is equal to 30 times 10 to the power 3 multiplied by izz divided by 6.339. And then again, this minus, but we realize that this is equal to 0. So 60 times 10 to the power 3 mz multiplied by x distance. The x distance equal to 0. Right? So divide by 19.339. So this will be equal to 30 power 3 times 1.5 by 6.339 minus 7.099 times 10 to the power 3 psi. Okay, so we have all the normal stress sorted out. Okay, so now we are going to view the shearing stress. So by viewing the shearing stress, let's get these figures over. Okay. Okay. So this is our Vx. Okay. And then this is our Vy. Or this is our, I cannot remember. I think this is our Vz. So our Vz, just to get the values over, it's equal to 1200. So we know that Vz is equal to 1200 pounds. Okay. So now we are going to find the formula that we're going to use. Again, you have to be very careful with this. Okay. It is this formula that we're going to apply now. Okay, it's this formula. So we know our Ix, our Iz. So what do we know about this formula? We know everything, even T is equal to 0.25 inches. Okay. So let's look at Vx. Okay, let's look at Vx. And Vx, we know that is under what? Box beam analysis. So we know that is going to be what? It's going to be based on 2Q. Okay, not 1Q. Box beam is 2Q, right? So if we look at point A, or let's look at elements first, okay? Let's look at element C first. Okay, let's look at element C first. Okay, element A is the easiest, C is not so straightforward. Okay. So element C, right, is exactly at the, if you look at element C, is exactly at the centroid.